So uh, I want you to imagine this tiny piece of black plastic. It costs like less than a penny. And the core design hasn't really changed in decades.
Yeah, and it's basically responsible for kickstarting millions of engineering careers.
Exactly. So today, our deep dive is all about the BC547 transistor.
Oh, man, the classic.
Right. For anyone who messes around with electronics, this thing is practically an old friend.
It really is. I mean, it's an NPN bipolar junction transistor, or,
Right.
BJT.
BJT, yeah. And we're really looking at the actual mechanics today, why this specific super cheap component remains this universal bridge between digital logic and physical action.
Which is pretty remarkable when you think about it. I mean, the sheer pace of obsolescence in electronics is crazy.
Yeah.
We have chips now packing billions of microscopic transistors.
Oh, yeah, billions.
But if you open up a prototyping kit today, you are still going to find a handful of discrete BC547s.
Just sitting right there in the box.
Always. Because it's just so incredibly reliable as either a simple electronic switch or a signal amplifier. Plus, they're available everywhere.
So let's talk about how this thing actually looks. It's got that classic half-cylinder shape, and the layout of the pins actually gives you a hint about the mechanics.
Right, the 3 pins.
Yeah, so if you hold it with the flat side facing you, the pins are collector on the left, base in the middle, and emitter on the right.
The famous CBE layout. And since it's an NPN junction, that base pin in the middle is actually this super thin layer of P-type silicon, basically sandwiched between 2 thicker layers of N-type silicon.
That was the whole key to how it works, right?
Exactly. That structural sandwich is everything. The P-type base essentially acts as this barrier, they call it a depletion region,
Right.
and that barrier normally just completely blocks electrons from flowing from the emitter over to the collector.
So, you always hear that tired analogy of a water valve, where you just turn a handle to let water through.
Right.
But really, we should think of the base as more of a toll gate governed by electrical pressure.
That's a much better way to put it.
Because if you apply a tiny positive voltage to that base pin, you are actually altering the semiconductor physics. You shrink that barrier down.
Right, and once that gate drops, boom, a huge rush of electrons from the emitter can suddenly cross over to the collector.
And if you take away that base voltage,
The barrier shoots right back up, and the flow stops instantly.
boom, cut off.
Exactly. Which brings us to the 3 main modes. When the barrier is fully up, 0 voltage at the base, that's cutoff mode. Absolutely no current flows.
Like a completely closed valve.
Right, but then if you apply enough voltage to totally dissolve that barrier, you hit what's called saturation mode.
Meaning it's acting like a digital switch, right? The gate is wide open.
Exactly. Current flows freely, it's fully on in. But the real magic happens in active mode.
Oh, right, because it's proportional.
Yes. If you apply just a partial voltage to the base, you only partially lower that barrier.
So a tiny fluctuating electrical signal at the base, like say the super weak analog wave from a microphone, that causes the main collector emitter current to fluctuate in that exact same pattern.
Yeah, you get a perfectly magnified replica of the original signal. That's signal amplification right there.
It's just so elegant. But wait, I have to push back a little on this idea of a huge rush of electrons or a larger output.
Oh, okay, fair.
Because the BC547 has a pretty hard physical limit, right? The maximum collector current is only, what, 100 milliamps?
Yeah, just 100 milliamps.
So wait, if it opens the floodgates, can I use a BC547 to power like a massive robotic motor?
Oh, absolutely not. No, it would melt. It is strictly a low-power device.
So then why use it? If we have modern microcontrollers that do all our logic processing, why are we manually wiring up these little 100 milliamp transistors?
Because modern microcontrollers, like an Arduino or an ESP32 board, they operate on incredibly low power.
Right.
They only output signals of a few milliamps. They literally do not have the physical muscle to directly trigger a mechanical relay or, switch on a high-brightness LED array.
Oh, so they need a translator?
Exactly. The Arduino sends its tiny, say, 3 milliamp signal to the base of the BC547.
Which drops the toll gate.
Drops the gate. And that allows a completely separate, dedicated 100 milliamp power source to flow through the collector and actually engage the relay coil.
That makes total sense. It takes the electrical workload so the sensitive Arduino brain doesn't just fry.
Right. And since it's so standardized, if you need a slightly different voltage or switching speed, you just swap it for a sister component, like the 2N22282 or the BC548.
So simple. Master that one basic mechanism, just manipulating an invisible semiconductor barrier, and you can bridge the gap between tiny digital logic and real-world physical automation.
It's pretty empowering.
It really is.
Mhm.
It makes you wonder if understanding a piece of plastic that costs a fraction of a cent gives you that much control over your environment. How might decoding the other invisible mechanisms around us change the way you look at the incredibly complex devices sitting in your pocket right now?